Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Hi and welcome back to chapter 53. Now, I've had a few days between recordings now, so if you're watching this video after a gap or any time through this series, always remember to kind of remind yourselves of where you're at in the regulations. We are now in the selection and erection of equipment part 5, and we have just started chapter 53. 51 and 52. 51 covered common rules which apply to the entire content of part 5. 52 was selection and erection of wiring systems, and in that chapter, which we split into a few videos, we included wiring systems, but we also included cables and circuits. We also included connections and talked about proximity and things like that. So as you progress through these videos, always try to remind yourself of the actual intent of this book and intent of the section that we're looking into. That way, if you need to look at it in the future, or if you have a scenario, you can just obviously understand typically what the circumstance you have is and how the book will actually help you with that. In chapter 53, we're going to look at selection and erection of types of devices, and different types of devices have different purposes. So we're going to look at the need of devices for protection, the need for devices against isolation, a switching device, a control device, and a monitoring device. Now, they're all different devices, but if you think about those words specifically, you can understand now how they are all important and how there will be certain requirements for each consideration. Okay, with protection, we'll obviously be thinking about protection against electric shock and protection against fire. Now, isolation, we've already mentioned previously in the video, methods of switching, which were for isolation, mechanical maintenance, or emergency switching. We also had functional switching, and we had control switching. Now, so we're going to kind of go through these here. So to start us off with, where are we? Chapter 53. We've got protection, isolation, switching, control, and monitoring. And it starts with 530. There's a scope bit there, but it starts with 530.3, the general and common requirements. So, every item of equipment shall be selected and erected so as to allow compliance with the requirements stated in the following. So, the moving contacts of multi-pole switching devices marked for the connection of the neutral or midpoint may close before and after the other contacts. So, the closure can happen before or after other contacts. So it's obviously saying that there's no need for one to be ahead of the other with that. Switching device shall not be inserted in the neutral conductor alone. We've mentioned this a few times now, where we talk about the fact that we must not switch neutral as a single pole device. There was one exception to that, which we mentioned before, with regards to specific lighting controls with contactors within the actual luminaire itself. But the fundamental rule is line conductor is always switched single pole or multi-pole, but neutral must always be switched multi-pole with line. We never single pole switch neutral. Devices embodying more than one function, as defined in the fine regulations, will comply with the requirements for the chapter appropriate for each separate function. So if a device achieves isolation and protective, it must comply with the requirements of both isolation and protective, and one must not inhibit or affect the other. Equipment intended for protection only will not be provided for functional switching of circuits. So if you have a device that is there for protection only as a method, it would be considered as a effective switching device. Again, I mean, it depends on how you consider it to be a selective switching device. But if you think about that, equipment intended to be provided for protection only, even things like some fuse types. Yeah, they're not going to use them as a functional operation. 530.4, fixing of equipment. Take into account the manufacturer's instructions, if any. I don't like that, if any, really, because there should always be some form of manufacturer's instructions. The equipment shall be erected in such a way that the connections between the wiring and the equipment shall not be subject to undue stress or strain resulting from normal use of the equipment. Okay, again, we need to remember some of the first things that we talked about back in assessment, general characteristics, and all this stuff. The selection erection, we must make sure we are doing it for the normal use. Now, if it's considered that the way that it's selected and erected, and it's fixed, then later on it being used in a ineffective or inappropriate fashion results in the creation of risk. You can't be held accountable for that. However, you must remember that if you're going to install this equipment in a sports hall or a place with antisocial behaviour, then you're going to have to consider that risk as an external influence category, which we mentioned back in chapter 52. We looked at in appendix 5. So you can't put in a typical household type switch if it's in a location where there'll be a risk of impact on the regular. Now, obviously, I've done work in homes and sheltered homes where there have been people that regularly they're vulnerable and they regularly can damage property. And when I've done periodic inspections, I'll always assess for that, and I'll always ask the clients about any direct attention to electrical accessories, luminaires and things like that. But most often not, they're talking about doors and walls and stuff. But if it has ever happened, then they do upgrade that category. We mustn't select equipment where if its use in normal conditions will actually diminish its life. Now, with regards to the manufacturers, even if you get simple patches, there are holes that tell you where to fix it. Those are still considered as manufacturer's instructions. If you were to drill your own hole in an enclosure that was not provided by the manufacturer, you'd have to say to yourself, does the manufacturer actually support this method of erection? So you've got to make sure that anything that you install, anything you select, has been installed as designed for purpose. If it doesn't have a way to be installed the way you want to install it, it may not be the right selected item of equipment. You may need to find something else, something more suitable. Okay, it then says, unenclosed equipment shall be mounted in a suitable mounting box or enclosure in compliance with the relevant parts of BSEN 60670 or 62208 or other relevant standards such as BSEN 61439. Again, I'm not going to go through those standards and the specific requirements of every single one of them because there's no point, but it's got to be designed for purpose. So if you're going to install equipment in an enclosure, it has to be an equipment that actually is designed to have that equipment installed within it. Yeah, if your equipment has a thermal cycle, for example, you don't enclose it in something that will not actually allow a similar thermal cycle during use. Equipment such as circuit breakers, switches and socket outlets and control equipment may be installed on or in a cable trunking system complying with BSEN 50085. Wherever equipment is fixed on or in a cable trunking, skirting, trunking or in a moulding, it shall not be fixed on covers which can be removed inadvertently. So an inadvertent, such as the simple removing of a lidding or something like that. So that's the fixing of equipment. It's 531. Devices for protection against electric shock by ADS. So let's remember ADS, automatic disconnection of supply. This was one of the primary general protective measures that we discussed way back in chapter 41. Okay. So, devices for protection against electric shock by ADS shall be suitable for isolation in accordance with chapter 46 and section 537. Automatic reclosing of devices for protection against electric shock by ADS of supply shall only be installed in an associated part of the installation where access is restricted to instructed persons or skilled persons. So if you've had a device that's disconnected due to an ADS need, such as an earth fault loop, the device that opens shall require manual reclosing if it's in a typical homeowner environment or an ordinary person environment. If you're in a skilled or instructed environment where equipment can be monitored regularly and things, there can be a form of automatic closing of those contacts. Warning notice will be clearly displayed near the point of access to the associated part of the installation controlled by any auto reclosing device, indicating its automatic reclose function must be disengaged prior to entry. That makes sense. It then says, in a TN, TT or an IT system, the following protected devices may be used. We can use an overcurrent protective device in accordance with 531.2 or a residual current device in accordance with regulation 531.3. So overcurrent protected devices. When an overcurrent protected device is used for protection against electric shock by ADS, then it will be selected in accordance with section 533, which we'll come to very soon. For TN systems. In a TN system, overcurrent protected devices, when used as devices for fault protection. Okay, so let's remember that all these protective measures, including ADS, have to achieve basic and fault protection. And with regards to the basic protection, that was the insulation, the barriers, the enclosures. The fault protection was the combination of earthing, bonding, and the selection of a suitable protective device, which is what this is. That's why it says fault protection. If a certain equipment or certain parts of the installation, the maximum disconnection times in table 41.1 cannot be fulfilled by the overcurrent protected device, those parts shall be protected by an RCD in compliance with 531.3.5.2. We're going to come to that very soon, but it's basically saying if ADS isn't achievable, with regards to the earth fault loop impedance that was covered in chapter 41, then an RCD can be used to help support this. But we're going to look at this again in a bit, and there's something we need to be aware of at this point. It then says, in TNS systems, the neutral need not be disconnected if the supply conditions are such that the neutral conductor can be considered to be of a reliable earth potential, so of significantly low impedance between neutral and earth. So the TN system, obviously where we have the link between the neutral and the earth supply at the intake position, as long as we can assure that that significantly low impedance is there, then we do not have to have an isolating device on neutral, because there's no potential voltages there. If it was a TT system, there's a high impedance there. And we would always, as we said on the previous video, will have a multi-pole, 4-pole isolation in the 3-phase TT system. TT systems. Overcurrent devices may be used for fault protection provided that a suitably low value of ZS is permanently and reliably assured, so that in case of a fault, stripping of the overcurrent protected device in compliance with the required disconnection times is achieved. So what this is saying is, whilst we know that with a TN system where we have that low impedance that we should achieve the high fault current for the quick disconnection, we can also use an overcurrent device for the same practice and same principles with a TT system if we can verify that the ZS at the point of fault or point of circuit fault is low enough for the same requirements. So the ZS is low enough to achieve a fault current that's high enough, and it does say here though that we can rely on that value of ZS, because one of the issues with a TT system is using the earth electrode, and you can have varying values of earth electrode resistance through the seasons, through the year. So you may measure the ZS at one point and say that does establish an effectively high fault current to disconnect it, but in a drier, warmer time of the year where there's less moisture in the ground, it's likely the resistance would have peaked up and climbed up. So the regulation is there, but we very rarely put that into practice. Okay, we just wouldn't, because it's just harder to control. For the IT system, overcurrent devices, when used as devices for fault protection in the event of a second fault. Let's remind ourselves about the IT system. The IT system is a specialised earthing system where we establish a high impedance between the earth and the supply live conductors, so if there is an earth fault current flowing, so there is an earth fault condition, that high impedance results in a very, very low current, a current value that will not cause harm. The such current not causing harm will result in the protected device not being disconnected. So what we'll have with that circuit is a monitoring system, an alarm system, to actually raise people's awareness of this fault. But that does mean we'll still need to have sufficient protection against a second fault condition, which is what this is referring to. The second fault condition will have to have afforded protection, same as the principles for TN and TT systems. Okay, so basically an IT system works in the case that a first fault occurs, the high impedance results in low current, results in an alarmed scenario, but a second fault occurs, it behaves just like a TN or a TT system. We have RCDs. 531.3. Except where 531.3.1.201 applies, which is saying that for protection against electric shock, there's no requirement to turn the neutral off. You must disconnect all live conductors of the circuit. The protective conductor shall not pass through the sensor of the RCD except where this is unavoidable, for example, in the case of an armoured cable. In such exceptional cases, the protective conductor alone shall be passed again through the sensor, but in the reverse direction. The protective conductor shall be insulated and shall not be earthed either at the first or second passing through the sensor. This is a weird scenario. So what this is saying is, let's remind ourselves of how an RCD actually works in principle. So we'll have the two live conductors flowing through a coil, and that coil will obviously pick up any imbalance in current between those two conductors. So if this is line current flowing down to my load, then I'll have neutral flowing the current back, so they'll be flowing in opposite directions. That's how circuitry works. So, whilst we know that AC it changes, but it's always in the opposite direction when it's changed. So line goes one way, neutral goes the other through a coil, and when there's an imbalance in current, one of those is achieving less current or carrying less current than the other because some has shot current down to earth. That imbalance results in, current being induced into the coil, and then it picks it up as an RCD. What this is saying is, I should really draw this, it'll probably be easier to explain. What this is saying is, you've got your line going down, and you've got your neutral going up, but at the load, there's equipment leaking to earth, but within the cable, going through one coil, like an armour, the earth is also going through the coil. So instead of running like you know with an RCD, you run your two live conductors into the top of the RCD, and then your live conductors going out, and your earth is completely away from all that. This is saying that earth is with those going through the coil. I don't know. I've seen RCMs go around cables, but RCDs going around whole cables, sheath cables. I guess that's what they're referring to here. So if we had that scenario, we had let's say that line has I'm really tempted to draw this. Let me say that line takes 5 amp down, but neutral has just 3 amp going back. That means 2 amp is lost, and that 2 amp has gone to earth. But that earth is also going through that RCD, so that 2 amp on earth is also going that way. So you have 5 amp going down, then you have a 3 and a 2 going up, which is 5 up. So 5 down, 5 up, it doesn't detect the imbalance. So what it's saying is with your earth that takes your 2 up, you now need to go back down. So it takes the 2 up, and it takes the 2 back down through the coil again, and then goes up to its connection. So it's going to go like, the earth will go, current will go up through the RCD with the neutral, but the earth will go back down through the coil again, and it'll go out of that and up. So what's happening is you've got your 5 down the line, and you've got your 3 up the neutral, but then you've got your 2 up with the earth, which totals 5, so there's no imbalance, but then it comes back and cancels that 2 out. So it's deducting itself. It's something I probably would be better to draw, but it's something that is just stupid. And I would really like you to tell me if you've seen this before and taken a picture of it, because it's quite an interesting circumstance here. But if you understand the principle of RCDs and the theory behind it, it should make sense. It's all about achieving imbalance of current and making sure the leakage current to earth does not affect the amount of current being sensed by the RCD. Then we have this. This is obviously new in the 18th edition, and it's quite creative, I'd say. Unwanted tripping. This goes down to it aligns with things like division of installation and what we used to call discrimination, which we now call selectivity. It's about making sure that things aren't going to disconnect. So, residual current protected devices shall be selected and erected such as to limit the risk of unwanted tripping. The following will be considered. Subdivision of circuits to individual associated RCDs. These shall be selected and their circuits subdivided in such a way that any earth leakage current likely to occur during normal operation of the connected load will not cause unwanted tripping of the device. Now, I don't like that wording because to me, an earth leakage current is a current developed by a fault condition. I think that should say protective conductor current, such as it says below. But it's saying any earth leakage current to occur during normal operation. So, it's a bit weird. But okay. It will not cause unwanted tripping of the device. In order to avoid unwanted tripping by protective conductor currents and or earth leakage currents, maybe they're just throwing in both terms because they don't really know which one to use, the accumulation of such currents downstream of the RCD shall not be more than 30% of the rated residual operating current of the RCD. So, let's remember that this book is obviously, it's our book at design. It's our book at the design stage to design with. It's our book to offer us information on the design, and it's offering information for us when we periodically review installations to refer it. This is saying that if you're going to design a new installation and the client wants, socket circuits, here's I want sockets in that room and I want sockets in that room. It now says that we need to think, okay, well, what is the actual potential value of protective conductor current to the equipment plugged into the socket outlet? To which most clients will go, and if you say to them, okay, well, what are you going to buy? Let me know. Let me know the cumulative value of protective conductor current in the XYZ piece of electrical equipment so I can actually take a value of this and verify I'm not going to exceed 30% of the RCD. They'll just go, I haven't decided what I'm going to buy yet. Or they'll just go, I don't know. So there'll be some circumstances, laboratories and some other equipment where they've specified plant and they say, here's my plant, get me a circuit to that plant, then you can do this. That's absolutely fine. But what it's asking us to do is determine the value of protective conductor current at this point in the system to decide if we actually need more than one RCD. Which isn't a very practical way to approach it. I think for example, if I was to say, a computer room, like a school computer room, I would probably recommend installing a single circuit and have every socket outlet an RCD socket, probably. Or maybe 2 or 3 radials, just so there's a slight level of selectivity. Okay, and a bit of division. But I wouldn't be thinking of the values of protective conductor current leakage because this kind of stuff just isn't always offloaded by manufacturers. It's not always given you. Sometimes you have to measure it as you find it. But that's what they're saying. They're saying that we need to make sure that when we install an RCD for a circuit, to verify that it does not start nuisance tripping due to, again, cumulative protective conductor currents or maybe some earth leakage, we've got to verify that the amount of equipment being plugged into it does not give off all this protective conductor current that will result in this thing nuisance tripping. So again, it's more information that we probably should seek at the design stage if we can. We then have types of RCD. Different types of RCD exist. It's funny because a lot of electricians don't really think much about it. They just buy the stuff off the shelf, the typical AC RCD here. Depending on their behaviour in the presence of DC components and frequencies, the appropriate RCD shall be selected from the following, and it gives you a bit of a list. And I can think of a very good example that a colleague of mine came up with just recently, where a client of his bought a washing machine, and the washing machine actually gave off. Remember, anything that's got a rectifier in it's going to actually, utilise DC. There's going to be a potential leakage on this, DC leakage. And he had a washing machine, and it actually, in the manufacturing data, so in the manual, it actually said to connect it to a Type B, I think it was. It actually specified a Type B RCD. Obviously, the house fuse board change just went with the AC, but it actually, I think it may have been A, but I think it was B. It actually specified a type of RCD because of the consideration of the smooth DC coming up leaking through the rectifier. This kind of information may not be available until the client has selected equipment, until the client has selected their appliances and selected their plant and their machinery. we need this data at this point to select protective equipment. It's very hard to do that if we haven't got that information. So do make sure you identify there are varying different types of RCD, and they do different purposes. They are there for different purposes. Alright. 3.4, selection according to the accessibility of the installation. Alright. So if it's an AC installation with RCDs that are intended to be operated by ordinary persons, so this is again your homeowner, your typical your office worker, someone who isn't instructed or skilled, okay? Then we'll use RCDs to BSEN 61008 009 for RCBOs and 62423 for Type F and Type B RCCBs and RCBOs. It then says in 201, so this is again this is a UK specific regulation. If an RC may be operated by ordinary persons, it will be designed or installed so that it is not possible to modify or adjust the setting or the calibration of its rated current setting. So what it's saying is there should be no dials to adjust the range of the current or the range of the I delta N for the RCD. A delay mechanism, variable delay RCDs, things like that. Actually, it's illustrated right here. So here's a 60947-2 switch, and you've got these dials that'll adjust. There'll be factors for current, brim, 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 brim. And you'll have an adjustment on your RCD to introduce a delay to achieve selectivity. Yeah, ordinary persons should not be able to tamper with this because, again, I mean, you could install this device. What is this? This is a 3-phase. You could call this a 36K device, 250. But you could always, if you installed this on a cable that would only carry 160 amp. You'd actually install this, but you'd probably preset this down by a factor. You'd adjust the rating of it. And if a consumer came in and just started tampering with it because it's nuisance stripping, they can end up overrating it, or they can end up putting in a delay in an RCD that will result in a non-compliance with the automatic disconnection of supply requirements. So they should not be able to tamper with it. And if anyone does tamper with it, it should only be done by a tool or a key. And the consideration then is that they'll be skilled and instructed to be authorized to do as such. Okay, RCDs now. This 531.3.4 was all about accessibility. We're now going to go to 531.3.5, which is RCDs for fault protection. Alright. TN systems. RC shall be installed at the origin of that part of the installation to be protected. The requirements for unwanted tripping in accordance with 531.3.2 shall also be taken into account. The division of the PEN conductor into neutral conductor and protective conductor shall take place at the supply side of the RCD. So here's an illustration of your PEN conductor. So this is your TNC system. So you have a combined neutral and earth. Unless they were going to install an RCD, here's the point of separation between the two. This is saying the RCD must go over this side of that separation. Alright? That's what that's saying. On the load side of the RCD, connection between the protective and neutral conductors is not permitted. So once this RCD has been installed, connection between these two is not permitted. You've probably seen this before. If you have equipment running and you have obviously a neutral currents flowing through it, short it to earth, RCD disconnects. I would be lying if I've not said I've used that method as a way to identify a circuit before. But yeah, So, positioning of the RCD with the PEN conductor there. With the TT system, at the origin of the part installation to be protected, And the requirements for unwanted tripping to 531.3.2 shall also be taken into account. Okay. We then have the rated residual operating current value, I delta N, of the RCD shall not exceed the I delta N corresponding to the maximum value of earth resistance RA to the exposed conductive parts, taking into account the possible seasonal variations, including the soil's freezing and drying, of the part of the installation protected by this device as shown in table 53.1, where RA is the sum of the resistance in ohms of the earth electrode and the protective conductor connecting it to the exposed conductive parts. In English, what this means is to determine a value of RCD rating, I delta, we need to say measure the value of RA, and there's a magic number that's not illustrated on this page. Yeah, we've seen a formula before, back in part 4, Ohm's law, and we need to remember that when we touch on RCDs and TT systems, we're verifying that the person in the location is exposed to the values of voltage, and so we make sure that the potential voltages there do not exceed what we think is the value of voltage that could harm persons. So that's 50 volts. So when you're looking at a table and you're thinking, how's this add up? What you've got to say to yourself is, right, 50 volts is the maximum. So if I say, right, I have 50 volts, and they're on the shelf, they've made an RCD at 20 amp. Well, 50 volts, Ohm's law, over a current of 20 amp, what is the value of resistance that would be needed? 2.5. Okay, think about that. 2.5 times 20 is 50. Yeah, that's how the resistances here are calculated. Yeah, it's not too distant from the principles of earthing and bonding that we've mentioned before. Okay, so to determine what the I delta N of your installation on a TT system at the origin of the supply shall be, we don't say, oh, it's 100, oh, it's 200, oh, it's 300, oh, it's 30. Yeah, we should take a value of RA, of earth electrode resistance, consider the seasonal variations, yeah, and it's 50 volts over that, and we find the next device closest to that. Yeah, or you can always say, well, I have a 30 milliamp, let me take a measurement and see what I get. The problem is, if you go with 30 milliamp as an everyday answer, then you've got to consider the selectivity issues and the continuity of supply issues. On TT systems, it's not, it's always good to try to install an RCD that is suitable for the installation. Let's remember that, fire protection is 300 milliamp. So we need to make sure we try to be sensible. We'll take an electrode resistance measurement, and we'll do 50 volts over that, and then we'll get the next device that will allow for that value of RA. So it might be 500 milliamp, 300 milliamp or so, and that's not a problem. Do remember the seasonal variation though. And that's that table there. Just because I haven't put it on the slide, this is a common question in the exam now. They'll give you a value of RA, which might not be exactly these, but you'll then go, oh well, if it's somewhere in between these, it's the next one up kind of thing. So be aware of that. 532 jumps a little bit. There's nothing great there though. No. So 532, this is devices protection against the risk of fire. We've got in locations where in accordance with chapter 42, that was protection against thermal effects. A particular risk of fire exists. Preventative protection measures against the risk of fire are required. This may also apply to other locations of the electrical installation depending on risk analysis. So it's got there for RCDs for the protection against the risk of fire. Key thing to remember, not exceeding 300 milliamp, and it will be installed at the origin of the installation for total isolation. Okay, key things to remember for fire and RCDs, 300 milliamp at the origin. With RCMs, they may be used as an alternative, provided that there is a location is supervised by one or more skilled instructed persons. So it's still 300 milliamp rating. You'll see it says that there, not exceed 300 milliamp, but there'll be an alarm system instead of a disconnection. Okay, which will do the same thing in principle. We then have the options of an installation monitoring system and internal arc fault protection in switchgear. And before we move away from 532, there's a last little reminder on the arc fault detection device, which doesn't actually give us much more information than what we had in chapter 42. It says, where specified, the arc fault detection device shall be installed at the origin of the final circuit to be protected. We knew that from chapter 42. And in AC single circuits not exceeding 230 volts. (533) Devices for protection against an overcurrent. Let's remember that an overcurrent can be a overload current or a fault current. Okay, but this is not an earth leakage current. Compliance with standards. A device for protection against overcurrent shall comply with one of the following. We have a list there of British standards. We have the BS88 fuse type, such as these. We have the 646, the 1362, such as the plugged-in ones there. The 3036s, which isn't here, but that's the semi-enclosed rewirable fuses we've seen before. The 60898s. 60947s, which we saw just not long ago. 61009s, which you know are RCBOs. And 62423s. It then says fuses. A fuse shall be arranged so that as to exclude the possibility of the fuse carrier making contact between conductive parts belonging to two adjacent fuse bases. So there'll be no potential contact between two adjacent fuse bases to that fuse. That makes a lot of sense. A fuse base using a screw-in fuse shall be connected so that the center contact is connected to the conductor from the supply and the shell contact is connected to the conductor to the load. Blah-de-blah-de-blah. 533.1.2.3. A fuse shall preferably be of the cartridge type. Where a semi-closed fuse is selected, though, it shall be fitted with an element in accordance with the manufacturer's instructions, if any. In the absence of such instructions, we have to have further guidance, and that's given in this table here. And I've used this illustration just to show you what can happen if we don't follow the guidance. So this is a good example of a 5 amp that kept blowing, so they probably put a 15 amp in or something. So to just quickly study that table, this represents the nominal diameter wire size proportional to the rated current. So if I had a question asking me the nominal diameter size for a 30 amp BS3036 fuse, I would go 0.85 mil. Okay, that's the nominal diameter size of the fuse wire. Circuit breakers. This is just repeating a bit of what we saw with RCDs. It says where a circuit breaker may be operated by an ordinary person, it will be designed or installed so that it is not possible to modify or adjust its setting. Then we have overload protection wiring systems. Takes us back to the beginning of chapter 52 where we looked at that, and we looked at IB, IN, IZ. It's just repeating it. It's just supporting the process. It's supporting chapter 52 here. Okay, that takes us to 534. Devices for protection against over voltage. Let's remind ourselves that an over voltage, this isn't a fault current, this isn't a overcurrent or anything like that. This is a phenomena that can occur often from two sources. One would be a manual event such as heavily inductive switching or things like that, or a fault in the low voltage circuit resulting in a fault in the high voltage circuit. We saw all that in chapter 44. But this is just an example of your AC waveform with a impulse voltage that is typical to these kind of equipment, or these kind of fault causes. The other one was lightning, and lightning, obviously, as you can see here, is significantly higher. Yeah, but very, very short. Very, very short duration. So there's been a new approach with this. Okay. So, it contains provisions for the application of voltage limitation in order to obtain insulation coordination in the cases described in sections 443 before. This section focuses mainly on the requirements for the selection and erection of SPDs for protecting against transient overvoltages where required by section 443 or otherwise stated. It then mentions BSEN 62305 and 61643. This is obviously from the lightning area. This series of standards deals with the protection against the effects of direct lightning strokes or strokes near the supply system. Both documents use this with SPDs. The selection of SPDs is done by what they call the lightning protection zone concept, which is illustrated here. Now, if you think back to if you think back all the way back to when we talked about this in 443, in chapter 44, we mentioned that we had categories of or boundaries within this site. So the equipment closest to the supply had category 1, and then we had category 2 and category 3 and category 4. Category 1 was actually furthest in. Category 4 is the closest out to the actual harm. It's a similar concept here. So what we consider is the potential sources of this overvoltage. So we mentioned that if you had a lightning strike, it will go down to Earth, but then it could be induced. That voltage that goes down to Earth is looking for an Earth, and if you have lightning strike, let me just use this illustration quickly to show you this. If you have lightning strike an overhead line or a transformer, it's going to send this voltage down, and it's looking for an Earth. And whilst there'll be an Earth at the transmission end for obviously the network, here your Earth is locally sourced. So when lightning and voltage hit this, they're going to be going down to that Earth. Once this voltage has gone underground into the mass of Earth, it starts to lose energy, it starts to disperse, but it's just it's seeking for a better Earth, because ground is, it's not brilliant, it's not a brilliant conductor for the voltage. And if there's any cables underground, or anything that's underground like pipes, or telecoms, or power lines, antennas, they're potentially going to induce that voltage, because they're going to be running underground, and then as this voltage goes along, it'll induce that voltage into that, and at the end of those is either a CPC being connected to a main earthing terminal to an earth reference, or there'll be a main protected bonding conductor to the pipework, again going to the main earthing terminal to a 0-volt reference. So quite often the risk here is when we have these voltages coming in from a lightning strike, they're looking to come back in. They come in, they go down, but they try to come back into our system through our earthing. So what we need to do is we need to decide, well, where is the boundary, where is the biggest risk, and what type of SPD do we put there? And then we go in, there's, lesser need for an SPD, but, there'll be one, but it'll be of less energy need and maybe of quicker dispersion. And we did cover this before in chapter 44, if you wanted to refresh yourselves on this at the moment. So we have this boundary zone illustrated there. And so what it's saying is we have an SPD installed at lightning protection zone 0 and 1 for lightning current protection. So that's typically going to be your type 1 SPD, which we said in chapter 44 was the one that's going to take all that energy. It's going to try and at least halve it within a fairly short time, but not the quickest time that all SPDs operate at. But it'll try and take a lot of that energy and then let through some energy to then be handled by an SPD further down. We have lightning protection zones 1 and 2 for over voltage protection. So not lightning current protection, but over voltage protection. So this is behind the first line of defense. It's now another line of defense on sub-distribution equipment and assembly equipment. And there's also illustration of extraneous conductive parts. But hopefully if you study that drawing, you can kind of understand what we're saying here with regards to boundaries. This illustration is again in your on-site guide. They are still in the on-site guide. They have not yet come into the regulations book though. So that's the line protection zone concept. Now there is some further illustrations on this. You have an figure. Page 162. You've got figure 534.2, an example of the installation of Type 1, 2, and Type 3 SPDs respectively. And so it says there the Type 1 and or Type 2 is at the origin of the installation or at the main board. It then says the Type 2 or Type 3 is at sub-distribution boards, and then the Type 3 is most likely close to your sensitive equipment. You have different connection types illustrated here. I mean, I strongly suggest you observe the manufacturer's requirements with connection types anyway, but it does illustrate different connection types with regards to the configuration that is required. CT1 and CT2. Basically, a 4+0 configuration or a 3+1. Depending on the positioning of an RCD would also determine your connection type as well. Trying to not to go into too much depth, to be honest, with the SPDs, because it's probably going to require a dedicated video to understand some of this. But we've got, similar to chapter 44, we have the impulse withstand voltages. We've got some data here on the configuration and the minimum required UC of the SPD depending on the supply system's configuration, and impulse discharge is mentioned there with supply systems. And then table 534.4 I think would be the most useful one, which suggests different connecting types depending on the supply system being single phase or three phase, and where the connection is between lines or between line and earth or neutral and earth. So you can see a three phase connection type 2 would be used between neutral and earth. Okay, and it gives you a value there. .4.5 coordination. They'll be selected and erected such as to provide coordination and operation by reference to the manufacturer's instructions. We then have selection of SPDs with regards to the short circuit current rating. As stated by the manufacturer, will not be lower than the maximum prospective short circuit current at the connection point of the SPD assembly. So it's relative to the prospective fault current, or the short circuit part of the prospective fault current test. .4.7 in conjunction with RCDs. So we have the connection arrangements here with interruption ratings, and we have overcurrent protection. Just different configurations. .4.7 SPD installation in conjunction with an RCD. If an SPD is installed in accordance with 534.4.1 on the load side of an RCD, the RCD having an immunity to surge currents of at least 3 kA. Type S time delay RCDs will achieve that. There's a bit on critical length of the conductors for the SPDs as well. We have maximum lengths there. With regards to this, it doesn't matter how with regards to connecting an SPD, we have to have critical lengths because the size of the conductors doesn't really affect it. It's to do with the actual inductive effect of that value of voltage that's going to be there. So we have to minimize the length as short as practicable. So there's examples of the different connection types there. No difference to the previous regulations, really. The connecting conductors between SPDs and the main earthing terminal or the protective conductor shall have a cross-sectional area not less than 6 mm copper for type 2 and 16 mm copper for type 1. And it says referring to 433.3.1, Conductors connecting the SPDs and the overcurrent protected device to live conductors shall be rated to withstand the prospective short circuit current to be expected and will have a size not less than 2.5 for type 2 and 6mm for type 1. I'm tempted to do a dedicated video on this because, to be honest, this content may completely change again by Amendment 1, and I can easily spend 3 hours talking about that stuff. So what I might do is add a bolt-on video later, which I can then just purge and update every time it needs it. I think I might do that. 535. Devices protection against undervoltage. So an undervoltage protection hang on. An undervoltage protected device is a device that will identify a loss of a phase, such as a 3-phase motor starter. You know, you lose L2 and then all power goes off. Right. Well, the main thing to notice about this really is it says that we set as follows: direct operating under voltage release, low value of the relay operating voltage, high value of the relay operating voltage, time delay if required, indirect operating under voltage release for the lower value and the higher value, and automatic. So you can see there are three recognized methods: direct, an indirect, or an automatic reclosing. The characteristics of the protected device against undervoltage shall be coordinated with the requirements in the relevant standards for switching on inrush operation and switching off for equipment. Nothing really exciting there, to be honest. 536 though, coordination. Yeah, this talks more about the need for effective decision making. So the section covers coordination in the case of fault and overload conditions, and also takes into consideration aspects of section 133 relevant to the coordination of electrical devices as follows. Let's remind ourselves of 133, which was, a fundamental principle. That is the general selection of equipment, appropriate British harmonised standard, and then you've got the characteristics, voltage, current and frequency there. Okay. Section 536 does not provide requirements for the selection of an electrical device alone, but provides requirements for the selection of electrical devices to achieve electrical coordination between them. The requirements also cover aspects of continuity of supply of the installation. So the coordination requirements for selecting electrical devices as covered by the following regulations: the mutual interaction between those devices shall be considered so that they do not adversely affect the safety of the installation. The coordination of the electrical devices considers in the case of short circuit, overload and residual current. Aspects for coordination of electrical devices are selectivity, short circuit protection and overload protection. Okay, so short circuit protection, we've got to consider the fact that if a short circuit was to occur, that the protective device will have a tolerance for the potential value of current. So, your typical prospective fault current, your prospective short circuit current, your prospective earth fault current, the value of current must be, not exceed that. We have the ICN and the ICS that you'll see in the on-site guide on this. With an overload, we need to make sure that if an overload is occurring, it does not occur for long duration. Low overloads of long duration should not occur. And residual currents, we've already mentioned this: nuisance, unwanted tripping, selectivity. Okay, so that's what they're trying to achieve here. And if I go through all of this content in 536, I'm going to be repeating myself a lot, but it's all about selectivity. Understanding the importance of selectivity with overcurrent protected devices. Okay, so if you look at for 536.1, you can see that there's a point of fault under overcurrent protected device 21. The fundamental thing is, if that fault occurs on that circuit on overcurrent protected device 21, overcurrent protected device 21 should be the disconnecting device. If overcurrent protected device 1 was to disconnect, then overcurrent protected device 22 would also be dead, and that is what we call poor discrimination, or, well, what we now say is insufficient selectivity. I hate that term. So we always want the point of isolation to be as close as we can to the event. There's interesting wording here. Where selectivity is required, verification shall be made either by a desk study. Okay, I guess that's kind of what I'm doing right now. Taking into account the relevant product standard and the manufacturer's literature, or appropriate software tools or information is provided by the manufacturer for the specific use, or tests in accordance with the applicable product standard or manufacturer's declaration. In case of a desk study where energy limitation curves are used to verify selectivity, account shall be taken of the voltage for which the curves are given. Then we have RCDs, same principle. We need to make sure that we have the RCD local to the point of fault. Another thing that we have, obviously, an issue with RCDs is if I have an RCD, RCD1 for example, as illustrated there, and RCDs 21 and 22, if RCD1 is just a 30 milliamp RCD type AC, and RCD21 is a 30 milliamp RCD type AC, but RCD22 is a 10 milliamp RCD type AC. So they're all type ACs. RCD1 and RCD21 are 30 milliamp, and RCD22 is 10. Now, if I had a fault, such as a cable being drilled through or crushing a cable on circuits 21 or 22, it's likely that RCD1 would trip because there's no selectivity between them. You must ensure that there's selectivity in this case. And so an RCD at the origin, or a distribution RCD, as we saw with the fire protection a minute ago, should really be of a type S, so of a time delay, so that there is a delay to allow a local RCD to operate. If the issue was due to accumulation of protective conductor currents, or an accumulation of gradual earth leakage, not a huge amount due to a fault condition, then likely the local RCD will operate first, because that would be the one that would trip up that imbalance. But again, if they're 30 and 30 though, no, the one close to the origin would also disconnect potentially. So do make sure you understand how selectivity works with RCDs. And then they just felt like they needed more pages in the regs book, because they're kind of repeating themselves with regards to whether you have overcurrent protected devices or RCBOs, or overcurrent protected devices and RCCBs, and RCCBs and RCBOs, and yeah. They could really squeeze that down, to be honest. It goes on. And then they have backup protection with overload relays, backup protection of switches, transfer switches. Okay. The key thing to remember with all of this section is it's all about protective device selectivity. Alright? Protective device selectivity. That's what all of this bit's about. Okay. I want to move on though, because that's just, I'm going to repeat myself so much there. I want to move on to 537. Because we're on the hour mark now on this video, and I want to, I don't want to make too many long videos. 537's isolation and switching. Now, there's a lot of stuff that we've already discussed here. So, the BS 7671 recognizes isolation, emergency switching, functional switching, mechanical maintenance as different methods of switching. And I showed you this table on a previous video, and it just gives you a list of devices and whether they are recognized as a device for isolation, a device for emergency switching, and etc. Okay. So what does it have? So 537.2, isolation devices. These will be the type for which isolation function is explicitly recognized by the relevant product standard, so the product standard will recognize it as an isolator. Semiconductor devices are not to be used as isolating devices. They'll be selected in accordance with the requirements which are based on the overvoltage categories. They'll be selected and or installed so as to prevent unwanted or unintentional closure. Most isolating devices should be of a type where we can prevent inadvertent closure. So we either have them in a locked cupboard, we have a key lock, or we use the lock-off procedure. We put a padlock on them and we lock them in the open position, as it mentions in the next regulation there. Each device used for isolation will be clearly identified by position or durable marking to indicate the installation or circuit it isolates. So, unless it's immediately on what it's isolating, there should be a label that says what it is doing and what it is not doing. It must be clear so that anyone who isolates it and then goes to work will know that does not cover their point of work. Okay, 537.3.2 is mechanical maintenance. Selection and erection of devices for switching off mechanical maintenance shall be in accordance with the following regulations to comply with regulation group 537.2, which was isolation. So they'll comply with isolation, but also they shall be inserted in the main supply circuit. Where a switch is provided for this purpose, it should be capable of cutting off the full load current of the relevant part of the installation. Interruption of a circuit for the control of mechanical movement is permitted only where a condition equivalent to the direct interruption of the main supply is provided by one of the following. So supplementary safeguards, such as mechanical retainers, or compliance with another standard for control measures to be used. And it gives you some examples there. Switching off mechanical measures may be achieved, for example, by one of the following: a multi-pole switch, circuit breaker, a plug and socket. They will require manual operation. The open position of the contacts of the device shall be visible or be clearly and reliably indicated. The indication required by this regulation may be achieved by the use of the symbols O and I or 0 and I to indicate the open and closed positions respectively. So it's recognised that when you have switching mechanical maintenance, it's clearly indicated on, off, or 0 and I. So there's a status indication there. Okay. 537.3.3 emergency switching. So this is selection and erection of devices for emergency switching off shall be in accordance with the following regulations and 537.2, which was isolation. So they all need to comply with isolation, basically. It must be capable of breaking the full load current. It will consist of one switching device cutting off the supply or a combination of devices cutting off the one supply. A plug and socket outlet shall not be used as a means of emergency switching. Kind of makes sense. The means of operating handle or push button devices for emergency switching off shall be clearly identified, preferably by colour. If a colour is used, it will be red with a contrasting background, such as yellow. Now, it's important to understand that that's not an accident. They do have a red on yellow contrasting background so that it makes it pop. This photo is not a very good light for the switch, but you can kind of make understanding of that there. The reason why that quite often you'll see that red on a yellow instead of red on anything else is quite often in lower light the yellow helps the red pop and stand out. The means of operating shall be readily accessible at places where a danger might occur and where appropriate at any additional remote position for which the danger can be removed. The means of operation of a device for emergency switching off shall be capable of latching in the off position. That's a very common question. A device for emergency switching shall be a device that latches in the off, unless both means of operation, switching and for re-energization, are under control of the same person. The release of an emergency switching device will not be shall not re-energize the relevant part of the installation. Okay. Firefighter switch. BSCN 6066926 60947-3. It should be provided in low voltage circuits supplying outdoor lighting installations operating at a voltage in excess of low voltage, such as neon lighting and things like that. Indoor discharge lighting, again with similar voltages. Every outdoor installation on single premises should, wherever practicable, be controlled by a single switch. Let's think about the firefighter for a second. They want to go to one point. Similarly, every internal installation in each premise should be controlled by a single switch, independent of the switch for outdoor. They will comply with the following requirements where applicable. For an outdoor, it will be outside the building and adjacent to the equipment, or alternatively, a notice indicating its position should be placed adjacent to the equipment, and a notice should be fixed near the switch so as to render it clearly distinguishable. For an indoor, it will be the lobby, the point where you enter the building. The switch should be placed in a conspicuous position, reasonably accessible to firefighters, at not more than 2.75 meters from the ground or the standing point beneath the switch. So they need to obviously get underneath it and knock it off. It will be clearly visible, accessible, and marked to indicate the installation or part of the installation which it controls. The phone information shall be distinctly and durably marked on the firefighter's switch in a position where it can be clearly seen by a person standing on the ground at the intended site without opening the enclosure and when the switch is installed. On and off positions, the letters not less than 10 millimeters high, and letters reading firefighter switch or fire switch in letters not less than 10 millimeters high. Once installed, the handle off position will be up. So down is on, up is off. And to finish off Chapter 53, we have monitoring systems, monitoring devices. Installation monitoring devices for IT systems. We've talked about IT systems quite a bit now. We've mentioned the IMD, the installation monitoring device. An IMD is intended to permanently monitor the installation resistance of an IT system and provide an alarm where the installation resistance, RF, is below the response value of RA. Examples of these systems would be an electrical installation, a mobile generator, or a safety service. Mobile generator, we're going to see later on in part 7 with mobile transportable units that some of them will have their onboard IT system. IMDs will be installed as close as practicable to the origin of the part of the installation to be monitored. Instructions shall be provided indicating that the IMD detects an installation fault to earth. Installation faults shall be located and eliminated in order to restore the normal operating conditions with the shortest practicable delay. Where the IT system is used for continuity of supply, the occurrence of the first installation fault shall be indicated at a suitable location so it is audible and or visible by instructed or skilled persons. So if this IMD is installed maybe in an operating theatre or in a data centre, it needs to ensure continuity of supply. So a single fault occurs, we don't want the second fault to occur because that's a disconnecting fault. We want to make sure that single fault results in an IMD identifying it, hitting an alarm system, which then for a person who is occupying that area, who is skilled or instructed, will be prepared to either, remove the fault or to remove the load to another supply. It's recommended to use an IMD that signals an interruption of the measurement connections to the system, conductors, and earth. Installation of the IMD. Where a neutral conductor is distributed, the installation monitoring device may be connected to the neutral conductor. In this case, no overcurrent to the device shall be inserted in the conductor to the IMD. It will be connected symmetrically or unipolarly between the live conductors and earth, or the protective earth connections or reference point for the protective equipotential bonding. Where the neutral conductor is not distributed, the line terminal of the IMD will be connected to either an artificial neutral point within the three impedances connected to the line, or to the line conductor. Previous questions, those ones that I've seen. Okay. And then the other type of monitoring device that we have in here is the RCM, the residual current monitor. Alright, and that's quite quick and short there. An RCM permanently monitors leakage and fault currents to Earth of the downstream installation or part thereof, and is intended to inform the user about the level of these currents of that part of the installation being monitored. They're not intended to provide protection against electric shock, because they are a detecting device, they are not a disconnection device. They just detect. When RCD is installed upstream of the RCM, it is recommended that the RCM be set to a residual actuating current no higher than half of the rated residual operating current I delta N of the RCD. That's changed from prior. It used to be a third. It's now changed. It is recommended that RCMs are installed at the origin of the outgoing circuits and they will initiate an audible or visual signal which shall continue as long as the fault persists. So, similar principles in IMD, but they work on on a residual current leakage monitoring structure instead. Okay. You've got then a nice table in Annex A53 on page 188, which kind of is a bit like the switching table. It kind of gives us device functions and coordination. So if we were to say, can an RCBO be used to provide switching only? No. Can a contactor be used to provide overload protection? No. So that's just a fairly simple table to navigate. Okay, and then there's the last little bit on coordination, selectivity, and possible fault currents in systems with semiconductors. That's going to close chapter 53 though, and it's all about selection and erection of devices, protected devices, monitoring devices, switching devices, isolation devices, all of that. The next chapter, chapter 54, we're going to look at earthing and bonding conductors, earthing sizes, bonding sizes, and we'll talk about electrodes a bit. I'll see you in that one.